Okay, we're in 3.3 now. We're talking about a specific type of logical connective called a conditional. And this is a very familiar one just from common language. These are statements that come in the form of if-then. So to give you some examples of things that we're going to be calling conditionals, here's a few statements. If I study all night, then I will pass my test. If the speed limit is 65 miles per hour, then no vehicle will exceed 65 miles per hour. If the sky is blue, then I will eat a sandwich. Okay, these are all examples of conditionals, all examples of if-then statements, even if they don't seem to make any sense. So for example, this first one, if I study all night, then I will pass my test. That seems like a reasonable conditional to make. It's not necessarily, or if-then statement to make. It's not necessarily true. There's been plenty of people who've studied all night the night before a test and failed their test, but it seems pretty reasonable. If the speed limit is 65 miles per hour, then no vehicle will exceed 65 miles per hour. We know that's not true. People speed. However, as a logical statement, it's a valid statement to make. It has a truth value. It is either true or it is false. My guess is that this would be false in general. If the sky is blue, then I will eat a sandwich. This is an if-then statement. The two statements involved here, the sky is blue and I will eat a sandwich, don't seem to be related, but that doesn't really matter because it's still a statement that could be made. Okay, and I'll mention this again later, we don't want to fall into the trap of thinking that if-then statements always imply some kind of cause and effect relationship. Oftentimes they do, but they're not required to. So again, we'll address that later. Now, there's a number of statements that are not necessarily written in the form of this if-then type of statement, but they could be rewritten in that form. So I like to call these conditionals in disguise. To give you an example, a couple of examples actually, we want to take the given statements here and here and rewrite them in if-then form so that we can see that they are in fact conditionals. Starting with this one, cheaters never prosper. It doesn't look like it's written in if-then form, but notice if I were to say, if a person is a cheater, then they will never prosper. So these two statements are saying the same thing, except one of them is put in if-then form. So this thing right here, this statement, cheaters never prosper, can be thought of as a conditional because it has a form that conditionals are more typically put in. Down here, it is easy to win at chess when your opponent is 3 years old. Naturally, yeah. How can we put this in if-then form? Well, this one's kind of interesting because to put it in if-then form, it makes the most sense to actually switch the order that the two component statements appear in. If your opponent is 3 years old, then it is easy to win at chess. Okay, that's probably the most natural way to write that. But notice the statement that appeared at the end of the previous statement is now the one that I'm writing first in my if-then statement. So sometimes it's more logical to do it that way. Sometimes you'll get something that's almost an if-then form, but they leave the then off. So notice if I read this statement, if your opponent is 3 years old, comma, it is easy to win at chess, leaving that word then off. It's still a conditional, it's just in common language we tend to not always say the word then, even though it's kind of implied that it's there, and that's totally fine. So as we've been saying, these if-then statements, or statements that can be put into if-then form, are called conditionals. And because this is symbolic logic and this conditional thing is a logical connective, we need a symbol for it, and this is the symbol that we use. So that little right arrow, the way I would read this is if P, then Q. Or another way of thinking of the same thing is P implies Q. And oftentimes we'll say that, P implies Q. Still important to remember that a conditional statement, like the three examples we looked at the beginning of this section, does not necessarily imply a cause and effect relationship, even though the word implies seems to suggest that. So we will use that word sometimes, but the way we'll typically think of this is if P, then Q. The component statements P and Q in a conditional have special names. So the statement that comes after the word if, this P here, is called the antecedent for that conditional, and Q is the consequent. It's not too difficult to remember that one because consequent sounds like consequence. In a conditional, we're sort of implying that Q is the consequence of P, if P, then Q. But, that's how I remember it anyways. So again, the conditional is a logical connective, just like a conjunction, a disjunction, or a negation. And if you remember in the previous section, for all three of those logical connectives, we came up with truth tables. And so we should be able to do the same thing for the conditional. But before we can jump straight to the truth table for this, we need to talk out some of the possible cases, because it's a little bit counterintuitive what happens in a conditional when the antecedent is false. So let's think about what it means to determine the truth value of a conditional statement like this one. And it turns out it's actually easier to analyze this by considering what it would take for a conditional to be false. So again, take a look at some common if-then statements. If I said this, if I study all night, then I will pass my test. And then after saying this, if I go and I do in fact study all night, but the next day I take my test and I fail it, was this statement true? Well, no, it wasn't true. This statement was saying that if I did the thing that I in fact did, then I should expect a passing grade on my test. And since that didn't happen, this was a lie. So that would have made this statement false. But breaking it down into its components, what we're having is a true antecedent. If I study all night is the antecedent, implying a false consequent. I will pass my test. That ended up being false. So in the case where a true statement implies a false statement, that conditional is false. It's a lie. So that's what it takes for a conditional to be false. A true P implying a false Q. But it turns out that's the only time a conditional statement can be false. Here's an example to consider. This is another conditional statement. If a number is an integer, then it is rational. You see the if-then in there. So again, if the number that I'm looking at is an integer, then I should be able to conclude that it's rational if this thing is going to be a true statement. However, what would it take for this to be false, or what would happen if my antecedent was false? There's a couple of cases I could look at. Let's suppose, for example, that the number that's being referenced here is the number 1/2. The number 1/2 is not an integer at all. It's a rational number. What does that example say about this conditional? Well, it doesn't prove it false, because if this were false, then the number that I chose should give me a true antecedent implying a false consequent, and the number that I have here doesn't give me a true antecedent, so I can't analyze it that way. What that would mean is that this statement is not false, so by default it has to be true. Remember, statements can only be true or false. They can't be both, and they can't be neither. So in the case where the antecedent is a false statement, the conditional will always be true. And that's even true if, taking this, looking at 1/2 again, in this case, the antecedent was false, but the consequent was true. 1/2 is a rational number. But even if the antecedent and the consequent are both false, if the number in question is the square root of 2, which is irrational, it's neither an integer nor is it a rational number, I still don't have a true statement implying a false statement, which is what it takes for this to be false. So in that case, this is not false, and by default it's true. That logic, which is understandably a little tricky to wrap your mind around when you hear it for the first time, leads to the following truth table. This is the truth table for a conditional. Notice I have the 4 combinations of P and Q's truth values: true, 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 false, false, true, false, false. And notice in my final column here, P implies Q, 3 out of the 4 truth values are true, and only 1 truth value comes out false. That is the case where a true statement is said to imply a false statement. That would make the conditional statement a lie or false. Okay? I mentioned this before, but I'm saying it again, and it's really important to notice that a conditional statement, P implies Q, does not actually imply a cause and effect relationship. So here's another example. If I win the lottery, the moon, then, I could say then here, then the moon will orbit the Earth. Is this statement true or false? Well, what's the antecedent? I win the lottery. That can be true or false. It will most likely be false. I will most likely never win the lottery. What's the consequent? The moon will orbit the Earth. That's true always. That's a guaranteed truth. That's definitely happening. So what rows in my truth table could this refer to? Well, if I win the lottery, then that antecedent P is true. And the consequent is always going to be true, no matter what. So in that case, I'm looking at true implies true, which is true. If I do not win the lottery, the much more likely case, the moon's still going to orbit the Earth. So we've sorry, did I say if I win or if I don't? I forget which one I just said. If I don't win the lottery, then the moon will still orbit the Earth. That's a false statement implying a true statement, which is still true. The conditional is true in both of those cases, but my winning the lottery has nothing to do with the moon orbiting the Earth. So that's where we have to be careful. Implications or conditionals can be true even if the antecedent and the consequent have nothing to actually do with each other. They frequently can imply a cause and effect relationship. It's just not a requirement. Okay? So let's do an actual example here, working with truth values, or truth tables. Or no, I'm sorry, truth values. We'll do the truth tables on the next page. So here we're going to assume that P is true and that Q and R are both false. And then we want to determine the truth value of this compound statement. P implies, and then in parentheses, not Q or R. Okay? So in order to do this truth table, I have this truth value. We want to substitute the truth values of P, Q, and R into their component statements here. So P is true. I'm going to write T for true. Implies not Q. Not. Well, Q and R are both false, so that would be not false. Or R, which is also false. Okay, so substituting the truth values in for those component statements. Now, I work within the parentheses first, and I handle negations before I handle other connectives. So not false is true. This simplifies to true, implies true or false. Okay? Now, I want to evaluate this disjunction, true or false. Remember how to analyze these statements. These compound statements are true anytime at least one of their component statements is true. Notice that that's the case. So this disjunction is going to be true. Now, true implies true. Is that a true compound statement? Is that a true conditional? Up here in our truth table, true implies true is a true conditional. So this gives me a truth value of true. It's weird talking through these examples because, again, I think I mentioned this before, it feels like I say the word true or the word false like 1,000 times in a row, and it's almost like it starts to lose its meaning after a while, but hopefully you can kind of see how this is almost like simplifying an algebraic expression just using the rules of symbolic logic. Here's a couple more examples. This time we're going to let T represent just any true statement, F represent any false statement, and we want to determine the truth value of these two examples here. So notice this is a conditional. I have the symbol for a conditional, but now I have T representing a true statement, and then an actual mathematical statement on the right that I can determine its truth value for. So 3 plus 5 equals 1 minus 6. Is that a true mathematical statement or is it a false statement? It's pretty easy to see that it's false because 3 plus 5 is is 8, and 1 minus 6 is negative 5, and 8 is definitely not equal to negative 5. And so this is the same thing as saying a true statement implies a false statement. And that's the one case where conditionals will come out to be false. Okay? So this is false. How about this? 3 is less than 2. So here's the antecedent. It's the statement that's appearing before the conditional symbol. 3 is less than 2 implies a false statement. Is 3 less than 2? No, it's definitely not. So that's a false statement, implying a false statement. And here's the case that I think is the most counterintuitive. This is true. Okay? False implies false is a true compound statement. That seems really bizarre because everything appears to be false here. How can this come out to be true? And the key is, again, to remember the only time a conditional statement can be false is if something true is implying something false in that statement. If the antecedent of our conditional statement is ever false, regardless of what the consequence says, the conditional always comes out true. And so that makes statements like this, once you've internalized and become comfortable with that rule, a little bit easier to analyze. As soon as I see a false or an F showing up here in my antecedent, I don't care what this is anymore because it's automatically going to be true. Okay? All right. Now we move on to a couple of truth tables involving conditionals. So starting with this guy, I have two component statements, P and Q, and so I'm going to end up with 4 rows, 2 to the second power. I need a column for P and a column for Q. And then again, if you remember the kind of order that we develop these columns in, look for any negations. So I have a not P showing up there. I'll need a column for that. Once you've handled all the negations, look for parentheses. I have a set of parentheses right here. So not P and Q. Actually, don't need the parentheses here. I just need to acknowledge that they came from parentheses. Finally, the only thing left to analyze is the conditional itself. I've handled all the parentheses, all the negations, all the other connectives have been accounted for, and so now we can write the actual compound statement. P implies not P and Q. So let's make some columns. Pardon the sloppiness, kind of scribbling out that parenthesis right there. All right. Now we know what these first 2 columns should look like because we've done these enough times. True, 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 false, false, true, false, false. And the third column is easy as well because it's a negation, so we just do the opposite truth value that we see in our P column. False, false, true, true. Okay. Now we get to our first compound statement where we have an and connective, a conjunction. And remember, in order for this to be true, we have to have both statements being true simultaneously. Notice also we're comparing these previous 2 columns. So I have true, false. They're not both true, so that would have to be a false statement. False, false. That gives me false. True, true. That would give me a true statement. False, true. That gives me a false statement. Okay? Now, we're at the column that we care about, the actual conditional, the given statement up here. P implies this conjunction that we found truth values for over here. So to make this a little bit easier, remember, conditionals will always be true if their antecedent is false. If P is false, it doesn't matter what happens in my consequent over here. This will necessarily be true. So going all the way over to my P column, 2 out of my 4 truth values that we're considering are false, which automatically makes these true. Notice I didn't even have to look in this column. Okay? Now, come back up here. P implies not P and Q. So this column implies this column. Comparing truth values, I have true implies false. Remember, that's the only time a consequent ever comes out to be false. And here, I have the same thing happening. True, once again, implies false. So that would be the truth table for that example. Okay? Not too bad. Let's try another one. down here, once again, P and Q are my only component statements, and so I'm going to have 4 rows as the previous example. P, Q. I see a negation for both a P and a Q in this compound statement, so I need a not P column and a not Q column. I also have 2 sets of parentheses, and so I'll need a column for each of those, P and not Q. And then not P implies Q. Okay? That takes care of all the negations. That takes care of all the sets of parentheses and the connectives within those. All that's left is the conditional that's outside of the parentheses. And so now I can write that statement. P and not Q implies not P implies Q. By the way, symbolically, we can understand this statement. It looks a little confusing, it looks like, or not confusing, but complicated. It seems like there's a lot going on. But it may be really difficult to try and think of an actual example of a statement that's constructed this way. This seems like a bizarre, it's hard to think of an English statement that we could write out in words that would have this form to it. But whether or not we can come up with an example in words, we know there's a system of rules that we've been working with that allows us to analyze it anyways. Okay, so let me construct my columns now. There's more columns in this one than the previous example. All right, P and Q, my first 2 columns, are the same as they always are. True, 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 false, false, true, false, false. Okay. Not P and not Q are also straightforward. Use the opposite of the truth values that we have in the corresponding column. So this becomes false, false, true, true. This is true, false over here. So it's going to flip and become false, true over here. Okay. Now in this column here, we have another conjunction. So it's an and statement. P and not Q. P is my first column. Not Q is my 4th column. And so I'm comparing these 2 columns here. And again, as a conjunction, if a false statement shows up anywhere, that's automatically false. So true, false gives me false. True, true gives me true. Okay. False, false gives me false. False, true gives me false. Okay. Next up, I have not P implies Q. So where is my not P column? It's here. Q is the column before it. But remember, the conditionals have a direction that's implied here. I need to remember which statement is the antecedent and which statement is the consequent. So I have to start from column 3 and then move to column 2. Remember, anywhere that my antecedent is false automatically gives me a true conditional. And my antecedent, not P, is false in these first 2 positions. So that's automatically going to make both of these true. What happens in the next 2 positions? True implies true. That's true. True implies false. That's false. Okay? So now we've done all of this work. We can finally get to our last column here. And notice it's using the previous 2 columns. Here's the antecedent. You can match it with this. Consequent matches with this, and so we're doing a conditional between these 2 columns. False implies true. We know that that's true. True implies true is true. False implies true is true because the antecedent is false, and then false implies false is true as well. Okay. Now we'll define. We'll give a definition for this term later, but this truth table gives us an example of something called a tautology. And tautologies are an important object of study in symbolic logic. Tautologies are compound statements that are always true, no matter what combination of truth values you have for the component statements. If it always comes out true, like it does here, then we can say that we have what's called a tautology. There is a corresponding term for if this is always false. We call those contradictions, which is a term that you should be aware of just from, being a person. People know what contradictions are just from kind of common language. But there is a symbolic logic definition for that. So both of those things we talk about in a later section. Let me go ahead and stop this video here. We'll pick up on the next example in the next video.